Welcome to this lecture. So before proceeding to the discussion of this lecture, let's first quickly recall what we have mentioned in the previous lecture. So in the previous lecture, we have defined the integration of measurable functions with respect to the domain side measure. Now this definition went through several steps. So the first that we considered was indicator functions, and the motivation for defining integrals of indicator functions was simply the area under the curve, which we simply took it as the area of the rectangle that is under the curve. Alright, so that was for the indicator functions. And then keeping the idea that whatever integration procedure we manage to define, it should be linear. So with that idea at hand, what we defined was that since the simple functions are linear combinations of indicators, so we should be able to specify the integration values of simple functions. So we extended by linearity. But then we know that any non-negative measurable function can be approximated from below by simple functions, non-negative simple functions. So what we did was that the area under this non-negative simple functions, that should increase to the area under the non-negative measurable function. So anyway, that is the idea. So if you still continue to think of the area under the curve as the value of the integral, then you must specify the value of the integral of a non-negative measurable function as the supremum of all possible integrals of simple functions which are below that given non-negative measurable function. So that was what we had used to define the integrals of non-negative measurable functions. And finally, for any general measurable function which could take positive or negative values, what we did is that we split the function into positive parts and negative parts. So we looked at the integrals of h plus and h minus separately. If at least one of them is finite, then what we said is that okay, so we can define the difference. So in the case when exactly one of them is finite and the other is infinite, we called it as quasi-integrable. So there is still the way of defining that integral which could be taking values plus or minus infinity. And the good case was when both h plus and h minus have the integrals which are finite, and then what we can consider is the difference, and then the integral of h will also be a certain finite quantity as per that description. So in this lecture, what we are going to do is to look at properties of such integration procedure. So one of the important thing that we have to keep in mind that we are yet to prove that the integration so defined is linear in structure. Okay, so we'll have to prove it as we go along. So let us move on to the slides and continue the discussion. Okay, so in the previous lecture we have defined this integral. So let's just formulate the notations for this lecture. So h will stand for this measurable function defined on some appropriate measurable space, and suppose you are given a measure on this domain side. Alright, so h is a real valued function measurable appropriately, and then you want to talk about this kind of an integration procedure. Alright, so first you note that the integration as you have defined in the previous lecture is not really easily computable. Alright, so again our target now is to understand the properties of this integration procedure so that our job in computing these integrals becomes easier. Okay, so you want to get hold of multiple nice properties which should help us in computing these integrals. Okay, so that's basically what we are planning to do now. Okay, so we start with this proposition that you take two measurable functions g and h defined as on this measurable space, and you assume that the integrals exist. Okay, so what do I mean by that? So if you consider the integration of g, then there are two possible cases under which the integral exists. So first case is when g is integrable, in which case the integral value is certain finite number, some real number. Otherwise, if g is quasi-integrable, even then the integral exists, but it takes certain values which is either plus infinity or minus infinity. Okay, a similar statement you can make for the function h. Okay, so with that at hand, so let's try to move on and try to prove certain nice properties. So the first property is about scalar multiplication. What we are saying is that if you have a measurable function h, if you multiply it by some scalar quantity c, which is some real number, then you know that this is also a measurable function. So what you hope to prove is that the integration of ch, that should also exist with respect to the measure mu, and the integral value should be equal to c times the value of h, c times the value of the integral of h. Okay, so that is basically the idea behind the scalar multiplication. So but how do you prove this here? So we again divide the argument into following cases to make the argument clearer. All right, so let's see. In the case that c is 0, if the scalar c is 0, then the function is identically the 0 function. So you can think of it as a simple function which is basically taking value 0 throughout the set omega. Okay, so then as per the description, integration of ch will be 0 because you are just multiplying by the scalar 0 and multiplying it with the measure of the whole set omega. But 0 times any real number or 0 times infinity is taken to be 0, so therefore this integration is 0. But what happens to this integration of c times the integral of h? So again, whatever integral value h has, it could be a real number, it could be minus infinity, it could be plus infinity. No matter what is the value, once you multiply by 0, it's 0. Okay, so therefore you have that required equality. So this equality holds when c is exactly equal to 0. Let's now consider the case when c is positive. Okay, so what happens now? So again, now you have to go through these several steps which was used for the definition of the integral. So start with the indicator function. So take a set in your domain side sigma field and look at the indicator of that set. So if h is of that form, then what is the integral? So put in h as indicator of a, so you are considering c times indicator a, and as per the description, this is nothing but c times the measure of a. But you can rewrite it as c times the integral of h because h is nothing but the indicator. Okay, so remember the indicator of a, if you integrate it, you just get back the measure. So that's what we are using now. So therefore this required equality holds when h is an indicator function. But then let's consider the case for simple functions. So if you now do the similar computation, you will exactly end up with a linear combination of these measures of the sets. Okay, and as long as the series or the summation that you are working with, as long as that makes sense, as long as infinity minus infinity does not appear together, you can immediately define the integral and verify this required equality. So it just extends from the usual calculations that you have already seen for the indicators. You just have to deal with the appropriate linear combinations, and that's it. So you get the result for simple functions. But then what do you do next? You go to non-negative and measurable functions. Appeal to the definition. So what do you do now? So you look at the definition where you are looking at all simple functions below the function c times h and looking at those integral values. So you are looking at all simple functions considering their integrals. Okay, so now, so that supremum quantity is this quantity. So here remember, as long as h is non-negative and c is positive, c times h is a non-negative measurable function. So that's what we are using here. Okay, but then observe that if you scale the simple functions that you are considering now by the constant 1 by c, so then what will happen? This will still remain a simple function, but these simple functions 1 by c times s, so that will be smaller than h. But then you look at this integration value, so you divide and multiply by constant c. So for simple functions you have already allowed this multiplication by scalar, so that's what we are using here. Okay, so you can multiply and divide by the same scalar which is positive. Then 1 by c times s is a simple function, so you can easily observe that that class of functions is nothing but in terms of this new notation that you look for all simple functions below h, call them as s tilde. So then you are just rewriting 1 by c times small s as s tilde, that's all. So you are just going from this supremum to this supremum. This is just a change in the indexing of the simple functions, but this supremum remains the same because the values remain the same. All right, so therefore let's look at this quantity now. So here you are multiplying all the terms here, all the integration values here by this positive quantity c, and you are considering supremums there. Okay, so you bring it out and that is nothing but the supremum of this set. But this is over this supremum is over all simple functions s tilde below h, and that is nothing but the integration of the non-negative measurable function h. So that's it. So therefore you have managed to bring out that constant c from inside the integration to the outside. Okay, that's all you wanted to prove, and therefore the result is now true for non-negative measurable functions. How do you do it for real valued measurable functions? You just have to observe that the positive part of ch, that c times h, is nothing but c times h plus. Okay, because c is positive, this equality is true. Again, as c is positive, for the similar reason, the negative part of ch is nothing but c times the negative part of h. Okay, so that's it. You identify it this way, and then for h plus and h minus, which are non-negative measurable functions, use the result that was just proved. So therefore you start with the integration of c times h, that is nothing but the difference of these two integrals of the positive parts of c times h and the negative parts of c times h. Okay, but then you have identified the positive part of c times h as this thing, c times the positive part of h, right? And similar identification for the negative part, and you now bring out the constant c, the scalar c, and that's it. So therefore you get the required relation that the c can be brought out from your integration as long as integration h d mu exists. Okay, so therefore you have managed to show that no matter what kind of measurable function you take, as long as the integration h d mu exists, integration ch d mu also will exist, and it will just be that c times the actual integration of h. Okay, so that's great. So you have managed to prove it for the cases when c is 0 and c is positive. But what happens when c is negative? In that case, observe that c times h, this function can be thought of as minus c times minus h. Okay, so minus c here is now a positive quantity. So c was given to be negative, so therefore minus c must be positive, but then h is given to be a measurable function, so minus h is also a measurable function. You just have to observe that now the positive part of c times h can be identified as the part given as this. So you look at the positive part of ch, that is nothing but this function now. So the positive part of minus c times minus h, but minus c is positive, so that will come out of that calculation. So you are just looking at minus c multiplied by the positive part of minus h, and check that this is nothing but minus c times the negative part of h. And similarly, the negative part of c times h, that function can be identified as minus c times the positive part of h. And the rest of the argument follows similar to the case above when c was positive. Okay, so you just look at now the integration of ch d mu, split it into the positive part and negative part, use this identification. Here h plus and h minus are non-negative measurable functions, and minus c is a positive constant. Just use that and you will immediately get the required relation. Okay, that's it. So you have managed to show that scalar multiplication works nicely with this integration procedure. But then we now go to a very important comparison type inequalities involving this integration procedure. We are looking at two functions now, h and g. Suppose you have that the function h is pointwise below the function g. Okay, so therefore pick any point small omega in your domain, look at the function values. If for all such points in the domain function value of h is below function value of g, then what we are saying is that the corresponding integrals will also satisfy the same relation. So therefore if h is less equal to g, then integration of h is less equal to integration of g. So how do you show this? So here we consider a simple case, we prove it in detail, that simple case, but the rest of the case we refer to a appropriate reference. Okay, so we first look at this simple case. So here we consider the case when h is non-negative, and since g is above the function h, g also becomes a non-negative measurable function. Great. So now consider the integrations for h and g separately. First look at the function h. What is the integration for this non-negative measurable function? What you have to do is to look at all simple functions below the function h. So look at such simple functions small s. But then since g is above h, immediately for all such simple functions you immediately have the inequality that the function values of this simple function small s lies between 0 and g. So this is automatically satisfied. So therefore any simple functions that is below h is also below the function g. But then there might be some simple functions which are below g, which is a bigger function. G is a bigger function. So therefore there might be some simple functions which are below g but need not be comparable with the function h. Okay. So therefore if you are looking at this class of simple functions that are below h, that is contained inside the class of simple functions that are below g, but there might be more functions, more simple functions below g. So that can happen. So that's it. So now for all such simple functions, since this is a smaller collection of functions, then whatever values you get out of integration, so these values are already contained in the right hand side set. Okay. So for any simple functions that is on the left hand side, that simple function is already in the right hand side. So therefore corresponding values of the integrations are already listed on the right hand side. So this is a containment. But therefore if you are going to look at the supremum of these two quantities, the left hand side will be smaller, right? So since you are looking at a bigger set on the right hand side, that quantity will be bigger, the supremum will be bigger. So the required inequality simply follows by taking supremum on both sides. Now if you allow the function h to take negative values, then that argument becomes a slightly more complicated. H might take positive or negative values, and then what you have to do is to split the cases into h plus and h minus and compare with the appropriate parts for g. Appropriate g plus and g minus. Okay. So the explicit calculation here is being skipped. This argument will go through, but the only problem is that you have to divide into several possible cases. You have to compare h plus with g, g plus and g minus and so on. So we are simply avoiding that case, but the argument will go through by comparing all these simple functions. If you are interested, please go take a look at the book by Robert B. Ashe and Catherine A. Dwyer-Reed. The book title is Probability and Measure Theory. The theorem number is 1.5.9. So this is the second edition of the book published by Academic Press. You might choose to take a look at the detailed proof there. Okay. But we are going ahead assuming that the result is true. Okay. So we can compare the integrals provided the original functions already satisfy that required relation. So then we now get very nice interesting inequalities following that inequality. Okay. So what we do is that we look at the integrations of h and mod h. So observe that given any measurable function h, the function mod h is always non-negative and measurable. This we have already observed earlier. But then you can consider the integration of mod h. So this is the integration of the non-negative and measurable function mod h. So in particular the integration of mod h will be something non-negative. Okay, so that's the observation we can make very easily. But now compare these functions. So since h falls between these functions minus mod h to plus mod h, then you can automatically compare the integral values. So what is the integration of minus mod h? It is nothing but minus of integration of mod h. And that is dominated from above by integration of h, simply by following that inequality. Again, since h is less equals to mod h, integration of h will be less equals to integration of mod h. That's it. You get both sided inequalities, and hence you get that mod of integration h, you get mod of integration h is less equals to integration of mod h. So this is a very simple inequality to prove as long as you have managed to compare any two arbitrary measurable functions and their integrations. Okay, great. So with this relation at hand, we can now make some very interesting comments. So here start with a h which is non-negative and integrable. So if h is already non-negative, then h minus, the negative part, is identically 0. So you don't have to worry about h minus. So h is equal to h plus here, right? So if h is non-negative, this is what is going to happen. Then integration of h is nothing but the integration of h plus, and that is a finite quantity provided that h is given to be integrable. Great. Then what is going to happen is that provided such a h, if you can get a arbitrary function g such that mod of g is dominated by h. Okay, so you are starting off with a arbitrary function g now, And if mod g gets dominated from above by this function, this non-negative function h, then you will immediately say that g plus is dominated by h, simply following this inequality that g plus is a non-negative function and it's dominated from above by mod g, but mod g is dominated by h. So therefore g plus is also dominated from h by above. Okay, great. A similar inequality holds for g minus. So g minus is also less equals to mod g, and if mod g is less equals to h, then g minus is also less equals to h. Great. So therefore you will immediately say that integration of g plus is less equals to integration of h, and since integration of h is finite, you will immediately say that integration of g plus is finite. Similarly, integration of g minus is finite because it's dominated from above by integration of h. So both these g plus and g minus have finite integrations. So therefore what you immediately say is that the function g is integrable, and you immediately also observed that g and mod g both are integrable here. Okay, so this is something interesting, that as long as you can dominate mod g by an integrable function h, you can immediately say that the function g is integrable. You don't have to separately verify the integrability of g. Okay, so if you can get a bound in terms of some known nice function h which is known to be integrable, then g has to be integrable. So this is some explicit condition that will allow you to check integrability in a slightly easier fashion. Okay, but then what is the relationship between integrability of g and mod g? So you make a partial statement here. We will come back to this statement later on once more in a later lecture. So what we are observing here is that if mod g is integrable, then we claim that g has to be integrable. Why? If mod g is already integrable, observe these inequalities that we have stated earlier. Forget about h. G plus is dominated by mod g, so therefore integration of g plus will be finite provided mod g is integrable. So this is a non-negative function, mod g is non-negative, and if it is integrable, that means integration of mod g is finite. So g plus has a finite integral as long as g plus gets dominated from above by mod g. So that's it. So therefore g plus has a finite integral. Similarly, g minus will also have a finite integral. So putting them together, you get the integrability of g. So therefore, to check that g is integrable, one sufficient condition is that mod g is integrable. Another sufficient condition is that you find some other nice function h which is integrable and check that the inequality mod g less equal to h holds. That's it. Great. So in all of these results that we have discussed so far, we have discussed this scalar multiplication and certain comparison inequalities. We are yet to discuss the linearity property of the integration. So that's, by that I mean that we would like to say that integration of g plus h is the addition of the separate integrations of g and h. But the problem is, as long as you do not prove this, you cannot use it in your argument. So in all these arguments, still we prove linearity, we have to be very careful, we cannot use linearity. Okay, so this is a caution that you should be taking care of. Alright, but once you prove the required linearity, then we can prove the converse of the statement in note 9. So what is note 9 again? So in note 9 we said that mod g is integrable implies g is integrable. We are going to show that g is integrable implies mod g is integrable. So this will follow once we prove the linearity of the integration property. Okay, so we will discuss these issues in later lectures, and we are going to continue looking at properties of measure theoretic integration in the next lecture. We stop here.